Hey guys, in this video we're going to be taking a look at the Basel problem. So the Basel problem is basically an infinite series of the reciprocals of square numbers. So in other words, if you have 1 plus 1 on 4 plus 1 on 9 plus 1 on 16 and so on and so forth, you can see the reciprocals of all these are squares. So in other words, this here would be 1 squared. This here would be 2 squared, and this would be 3 squared, and this would be 4 squared. So an easier way to write this is in sum notation. So you can capture all this information in a couple of lines. So the sum from n equals 1 to infinity on 1 on n squared. This here basically gives this entire sum. Right, so is there a way to assign a value to this? Well, there is. And they discovered that pi squared on 6 is equivalent to this infinite sum. Now, that's very hard to imagine, but if you took a calculator and you started adding up these terms by hand, you'll get pretty close to it. So pi squared on 6 is approximately 1.64. And if you took your time and added those terms, you'll get pretty close, but we found an exact answer for it. So in other words, we represent it as a fraction of an irrational number on the top all squared over a whole number. Now, how did we find this? Well, Euler found it, but today I'm going to be showing you another way how you can actually find this number. So in other words, we're going to be proving that this infinite sum is equivalent to pi squared on 6. So how would you even start this problem? Well, to start it, we're going to be taking a look at the Taylor series of sine x. So a Taylor series is basically representing a function as an infinite polynomial. So in other words, the Taylor series for sine x, so sine x is equivalent to x minus x cubed on 3 factorial plus x to the 5 on 5 factorial minus x to the 7 on 7 factorial, and it keeps going on forever. So you'll notice that all these terms are odd. So 1's odd, 3's odd, 5's odd, and 7's odd, and every second term is negative. So this is the Taylor series for sine x. Now to start this off, what we're going to do is divide everything by x. So we'll have sine x on this side. Divide this by x, we have just 1, minus x squared on 3 factorial, plus x to the 4 on 5 factorial, minus x to the 7 on 7 factorial. Oh, that's not 7, sorry, that's 6. Right, so every single term in this series has been divided by x. Now, what we're going to do is we're going to use the fundamental theorem of algebra. We're going to try and represent this entire polynomial as just roots. So recall, if you have, like, let's say x squared plus 2x, let's just try and think of one with whole solutions. So if you had two numbers multiplied, so if you had x squared minus 3x plus 15, that'd be minus 15, sorry. So if we have something like this, we can represent it as factors. So think of two numbers that multiply together give 15 and add together give negative 3. So x equals negative 5. And, oh, that's not true. Sorry, I've got to change that around. Let's change it to 10. And then x plus 2. So negative 5 times 2 gives you 10. And negative 5 plus 2 gives you 3. So we can represent this polynomial as a factor. What we're going to do is try and represent this entire infinite sum as factors as well. So the trick with this one is to take a look at this first term 1. So when we multiply this out, we agree we have to get negative 10 as our constant here. The only way we're going to get 1 there is if one of the numbers in our brackets, well, if every single number in every bracket is 1. So in other words, you have this scenario here. And this goes on forever till eventually the last digit, which is hard to imagine because it's infinite. Right, so let's just clear up what we've got here. So in order to make this factorizable, every single bracket needs to have a 1 in it. Because when you multiply it all up, we need to get this 1 out the front there. Righto. Now, what are the roots of this? So the roots are pretty much the solutions to this polynomial. Now, you're not going to do long division on this thing. You'll be here forever. You can't even guess any solutions to this because it's infinite amount. So what you can do is you can ignore this side for now and just try and solve this side here. What are the solutions for this? Well, you can't have x equals 0 because then you'd have 0 divided by 0. But what solutions for sine x can you have? Any multiple of pi. If you put in pi in there, you'll have 0. If you put in 2 pi, you'll have 0. And likewise, if you put in negative pi or negative 2 pi, you'll get 0. So the solutions for this side here are any multiples of pi where n is a discrete number. So that means whole numbers, so like negative 1, 1, 2, etc., etc. So what that means is all these roots here, that means if this is the solutions to this side, that must be the solutions to this side as well. So now we can take a look at our infinite polynomial again. So that means all of our solutions are pretty much multiples of pi, or one of multiples of pi. So that means these bits are going to be plus x on pi, plus x on 2 pi. Now you also have the negative, so I'm going to put the negative here as well, so minus x on pi. So this here, these are all valid solutions to our polynomial because multiples of pi are solutions to this. And this goes on forever, but I'm going to write out all the terms. Not all the terms, but you know what I mean, a couple of them. Let's just put some dots there now. So that's all those terms, and just to show the rest of them, we'll have it like this here. Righto. Now you're probably noticing these here, these pairs of numbers I've put next to each other are differences of squares, so we can represent it even better. Because since there's a difference of squares, we can represent this here as pretty much this, 1 minus x squared on pi squared. Because if you were to multiply this out, just these two brackets, you'll get this down here. And you can do the same with this one here. So you'll get 1 minus x squared on 4 pi squared. And so on and so forth. And you'll keep getting this here. Is equal to sine x over x. Righto. So hopefully that makes sense. So if you multiply that out there, you'll get this, 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 and this infinitely. Now let's just take a look if we were to multiply this out again. So now we've done that with the difference of squares. If we were to multiply all these together, do you agree? We're just going to take a look at the x squared terms for now. Because if we just take a look at the x squared terms, we can see there's starting to be a pattern emerge. So if I multiply this one by here, I'll get that. This one by here, this one, etc., etc. So do you agree if we multiply all these brackets out, we'll have all these terms. But let's take a look at just the x squared terms. We'll have this plus negative x squared on pi x squared plus negative x squared on 4 pi squared plus negative x squared on 9 pi squared. Now the reason I'm getting all these terms here is these are all the terms, and there's infinite amount of terms in here that all have an x squared with them. Now the reason I'm just looking at these ones is because you can see this is very similar to the pattern we're trying to solve. The 1 over the square numbers, do you agree this is almost 1 plus 1 on 4 plus 1 on 9, and if I kept going I'd have minus x squared on 16 pi squared next. But there's infinite amount of terms. This is our polynomial here, but I'm just taking a look at these ones. So if all I got to do is I've got to take out a factor of negative x squared, pretty much. Negative x squared on pi squared. So negative x squared. Now keep this, and there's all these other terms here if you multiply the polynomial out, but I'm just looking at these ones here in our infinite polynomial because it has our Basel function in it. So this would be 1 plus 1 on 4 plus 1 on 9 plus dot 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 infinite amount of times, and then the rest of the polynomial. So I'm only taking a look at a fraction of the polynomial. But we can see this here is our problem. This here is our Basel function. In other words, I could rewrite this as a sum. The infinite sum from n equals 1 to infinity on 1 on n squared. So I can replace that there. So I'll go dot 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 plus negative x squared on pi squared multiplied by the sum. That's a terrible sigma. N equals 1 to infinity on 1 on n squared plus dot 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 all those terms. And that's still equal to sine x. Sine x on x. Now, we agree that sine x on x is still equal to our infinite series that we had up before. So this series here. Just going to write it all out. I think that's that. Minus. It would be minus 6 pi on 7 factorial. Yep. So we agree that sine x is still equal to this from our terms up before. So that means this entire infinite polynomial that we have here should be equal to all of this. Now, that means the x squared term, in other words this term here, must be equivalent to this term here. In other words, we're equating coefficients. Because if you took out a factor of x squared, that means negative 1 on 3 factorial should be equal to negative 1 on pi squared times our infinite sum. Because there's no other x squared terms in this infinite series here, only this bit, and that must be equivalent to that because they're both equal to sine x. So what we have here is a really simple equation here. All we got to do is make this sum the subject of the formula. 3 factorial is 6. Pull the negative pi squared over there, and we get pi squared on 3 factorial is equal to our Basel function. Now 3 factorial is just 3 times 2 times 1, so that's 6. So therefore the sum from n equals 1 to infinity on 1 on the squared terms is equivalent to pi squared on 6. The negatives cancel because I had a negative here and a negative here, so those became positive. Righto. That's my solution for the Basel function. I hope you enjoyed this video. If you did, leave a thumbs up and subscribe.